Hello everyone, we will start the next lecture for this week. In this lecture, we will start with the multi-column radiative convective models. So, we have already seen the 1D RC models, and what is the framework of the 2D RC models? It is we set up the 1D models for one zone, we can set up the 2D models for different latitudinal zones. So, when we combine this with the energy balance model, we get a 2D model. How they may look like, we will see the next slide. So, this is the illustration of one latitude of our 2D zonal models, only one latitude. Okay. So, we have short wave and long wave radiation coming in, we have QL, which is the latent heat release. So, F solar coming in and F long wave going out. Then we have vertical heat. So, we have basically, I will first explain the environment. The environment is an ocean layer, which is mixed layer and the deep ocean. Then we have this white color, which is sea ice. Then we have land, in which we have grass, snow / ice, snow and ice. Okay. Now, depending on the latitude, we may have 0 snow, 0 ice, or 0 oceans, or 0 land. This is a case of percent area covered by land, percent area covered by oceans, and depending on where we are, this may change. Then we have atmospheric layers. So, we have solar radiation, short wave radiation going down. We have long wave radiation going up, we have some latent release in the atmosphere. These are our different atmospheric layers. Then we have the planetary boundary layer in the atmosphere. We may have latent heat release. We have AV and AH, which are the vertical heat transport and the horizontal heat transport. When we go up and up, we reach tropopause and stratopause. Then over land, we have the HL and HS. So, these are the latent heat fluxes of our land with and without snow, sensible heat fluxes for land with and without snow, and then sea ice and the ocean. Now, within the ocean itself, we have horizontal heat transport OH and the vertical heat transport OV. So, this is our description of the environment. Now, we can write the surface and atmospheric energy balances also. So, let us start with the land. So, for land surface, we have CL times T. So, heat capacity of land surface multiplied by the effective depth, del TL. So, del land surface temperature by dt is equal to Rg, which is the absorbed solar radiation, minus I minus HS minus HL. So, these are absorbed radiation minus the infrared emissions, infrared heat flux, sensible heat flux and the latent heat flux. So, this now tells us the land surface heat evolution. Likewise, we will have the atmospheric temperature evolution. So, if capital T is the atmospheric temperature, we have del T by del small t is equal to Qs, which is the solar radiation, plus Qi, long wave radiation received, latent heating QL, and a value A, which is the heating due to dynamic redistribution of energy, and this is more empirical. Now, we also have here the ocean and biosphere components, as I explained in the previous slide. So, the model includes 4 different surface types. The ocean model here has 2 components. One would be the climate model for the oceans, the other would be the ocean biosphere and chemistry model. Now, what is an ocean climate model? So, ocean climate model includes heat exchange with the atmosphere, not with the sea ice, with the atmosphere, and we will have prescribed ocean flows. So, OH, OV, which would be from observations. The surface heat fluxes are then simulated separately, for example, for Atlantic basin, for Indo-Pacific basins. The heat, as we have also seen in the previous lectures and as is simulated here, is transported from equator to the poles. Now, we also have, when we say biosphere components, we are looking at biomass and uptakes. So, how do we have the biomass and carbon uptake here? So, then ocean parameterization will include biological uptake of carbon. The reduction of atmospheric CO2 concentrations, if we are simulating, are included explicitly. Now, when we say includes biological uptake of carbon, so the carbon is sometimes, of course, is linked with the atmospheric carbon. So, the model will simulate the downward transport by phytoplankton, also the settling of the marine grazer feces. So, the grazer who have eaten substances here, when they ingest, then the feces will also have carbon and that will also go down. So, the phytoplankton itself is going down, and let us say the organisms that feed on phytoplankton or feed on other biological material, their feces will go down, that will also export or transport carbon. There is a simplified food web in which we have phytoplankton and then also detritus. Now, having this ocean biomass and ocean climate together with the atmospheric model allows for the simulation of key ocean atmosphere interactions on a latitudinally averaged basis. Now, when we look at the advective flows, we can have, so when we are looking at the advective flows, we will have the thermohaline circulations. So, for example, how we will have our circulations in North Atlantic and the thermohaline simulations. This is the pictorial diagram. We have the advective flows in sweat drops. We have the surface here. This is the mixed layer, then different ocean depths, and then these are bases: Arctic, Atlantic, Antarctic and Pacific. So, it turns, when we look at the flows, Atlantic is sort of interacting with major flows. So, it's interacting with the Arctic flows, also it's interacting with the Antarctic flows, and it's receiving also. And here we have this surface water is being added to here deep water. So, 9.4 plus 4.2 at the surface is going down and it's being added at this deep layer. So, this would be a deep water formation. And then we have going up in the Pacific, goes up, and this goes eventually to Atlantic and goes to Arctic, goes back to Atlantic. In general, North Atlantic is a very important component of the ocean conveyor belt. This thermohaline circulation is highly sensitive to the climate change, and actually it is also been evident in sort of the early climate, paleoclimatic records as well. Now, the long time scales of ocean and influence on climate means, if we were to model them in general circulation models, we will need to integrate these models for a very long time span. If we do that, then we will have to wait for a lot of actual time for the simulations to complete. So, this long time scale of evolution or influence make this kind of analysis more suitable for a study using intermediate complexity models, because we have not gone highly detailed and complex, but we have not gone highly simplified either. So, these intermediate models will give us a good compromise between the model detail or complexity and the integration time constraints. So, EMIC simulations of overturning circulation actually happen to fall within the range of TCM results. And what kind of results we are looking? So, for example, under CO2 doubling, so CO2 doubling, doubling of CO2 concentration, all different models of intermediate complexities, all of them predict an initial weakening of the thermohaline circulation. So, the circulation becomes slower. There is a maximum reduction after 100 to 300 years and after that there may be a recovery to a new equilibrium. So, all models predict weakening of circulation, reduction and then recovery to a new equilibrium. So, that was the circulation related effect. The models also, of course, as we saw, model the biology in terms of simplified biological process. In this case, we have the oceanic phytoplankton because they will basically assimilate CO2 or assimilate carbon, and then they may also lead to the transport of carbon to the bottom ocean sinks. So, in many of such models, a simple parameterization of oceanic phytoplankton is used. The models are generally latitudinally averaged, and the phytoplankton abundance in these models is related to the nutrient availability, then the limitations or the availability of light. So, all these will influence the phytoplankton growth. Then the mortality of phytoplankton, how fast they will die, and the respiration rates also. This system is represented by a set of coupled equations, this phytoplankton system. These are as follows. First is the rate of change of biomass of phytoplankton. So, B subscript P is the phytoplankton biomass. This is given as B multiplied by P max. So, the maximum production rate multiplied by a light limitation function. So, this is our maximum rate, but since the light is limited, if the light is limited and does not allow for maximum production, then we will have a light limitation function PFI multiplied by relation to the nutrient availability, in this case the nitrogen. So, organic nitrogen by, so actual organic nitrogen concentration by concentration plus the half saturation constant for nutrients, in this case nitrogen. Half saturation constant means the concentration at which the rate is half. So, n by n plus n would become 1 by 2, or sorry, k by k plus k will become half. So, this is the half saturation constant for nutrients. So, this is the production definition in a way, maximum rate multiplied by a limitation for light multiplied by a limitation for nutrients. So, this is the actual production minus respiration. So, respiration leads to decrease in biomass minus mortality because the phytoplankton will die. So, there is mortality. This all function will then lead to the calculation of evolution of biomass. Now, how is the detritus being formed in this cell? So, detritus is being formed by the phytoplankton dying. So, mortality rate m multiplied by the biomass. So, this much phytoplankton dying will add to the detritus in the column, and the detritus being formed will then sink down. So, minus settling rate of detritus multiplied by the concentration of detritus. So, dd by dt will be how much detritus is produced, which is mortality multiplied by phytoplankton biomass, minus the settling rate of detritus. So, settling rate multiplied by detritus concentration. So, dd by dt is equal to mbp minus sd. So, this is the coupled set of equations using which the phytoplankton biomass is modeled in the simplified intermediate complexity models. Of course, different models will give us different levels of complexity of nutrient limitations, or the equation for light limitation, the Fi can be anything. Maybe in addition to nitrogen, they can introduce iron, phosphorus, or any other limitation, any other micronutrient limitation also. But this is okay. We are going with one simplified representation here. Now, when we have the truncated spectral of the GCM models, and intermediate, and we have seen this a little bit in the previous lecture. So, the intermediate position in the climate modeling pyramid can be achieved by restricting a more complex model. So, here we have this is sort of the computing demand. So, units per simulated year. This is the dynamical completeness of the model. So, here we have the AGCM all embedded with all kinds of models which have very high completeness in terms of description, but the computing demand is very high. So, let us say order of 10 to 5 per simulated year. So, we have to wait forever for these kind of models to run. Then as we go to reduced, we have lesser computing demands and somehow but okay complexities. But then we go down on the other spectrum, we have the zonally averaged energy balance model. Computing demand is very low, we can probably compute by hand or a very simple code. So, the demand is low, but see the completeness of model is super low as well. Then we can have the statistical dynamical model and the truncated spectral model, which are somehow in between. Computing demand is almost 10 to the power 5 times or 6 times lower, and the completeness is less than half. So, this is a judgment how much we want to compromise and still have a reasonable computing demand. So, one approach is to severely truncate a global spectral model retaining only the lowest wave. So, this is we are looking at highly truncated model, and this figure essentially shows the trade-off between model performance, which is the completeness relative to a full scale GCM, and the computational effort. So, the computation effort. So, how much completeness we want and how much computational effort we can make. Now, severe truncation of a spectral model is equivalent to a coarsening of the spatial grid of a Cartesian grid atmospheric GCM. So, this is a coarser model, although level of complexity has a bit decreased, but not too much also. So, spectral truncation. So, this is spectral truncation, this is grid coarsening. Truncation is often less worse or less detrimental than the increase in grid scale, because the baroclinically unstable waves are better represented at low resolution, but the fundamental dynamics remain reasonably represented even under the strong spectral truncation. Truncated GCMs can outperform often the two-dimensional ST models because the eddy fluxes of momentum, heat and moisture are explicitly calculated and not parameterized by statistics. So, we are actually doing mechanistic calculations. The computational effort is about still 2 orders. So, 2 orders of magnitude lower than full GCM. So, instead of 100 days, it is going to take 1 day for a simulation as an example. So, that is 2 orders of magnitude. So, that is a good improvement. What is the performance and limitations more? When we look at loss of resolution, if we have a loss of resolution, we need more improved subgrid scale parameterizations, and we need to have a compensation for distortions in the energy cascade. So, when we are doing this kind of models, the models are mainly used for IAMs, integrated assessment modeling. So, how do we capture 3D climate models with reduced computational cost? What we do is, we represent the full 3-dimensional climate processes using the intermediate complexity models. So, our intermediate models will require much less computational time than full GCMs. One of our reference book introduces a model called SPEEDY, which is called Simplified Parameterizations Primitive Equation Dynamics. So, what is the characteristics for this particular model? Of course, there will be many other models, and like the student is free to explore any of these models and kind of develop their flavor. So, as we already mentioned, this is an intermediate complexity climate model. So, it has 8 vertical levels. When in our previous lectures, we had a model, the one-dimensional radiative convective model, 17 or 18 layers. This one has 8 vertical layers, and we have horizontal spectral truncation. So, 3.75 to 3.75 resolution degree resolution, or 2.5 degree to 2.5 degree resolution. In the radiation, there are different schemes in that the short wave has 2 spectral bands. So, instead of one full wavelength range for short wave, there will be 2 short wave ranges, and there are 4 wavelength spectral bands in the long wave radiation range also. So, instead of saying everything is one long wave, there are 4 bands for the long wave radiation. So, this model includes the parameterization of large scale condensations, the shallow and deep convection, short wave and long wave radiation, the surface fluxes of momentum, heat and surface fluxes of momentum, heat and moisture, and the vertical diffusion. The advantage in this model comes out as follows, that it turns out to be very well computationally efficient. And what do we mean? One model year is done in 60 minutes. That means 10 years, one model year in 6 minutes, which means 10 years in 60 minutes. So, 10 years within 1 hour. So, in 24 hours, it can run 240 years. So, in one day, 240 years can be run. If you wait for 10 days, we have run for 2400 years. So, that is a very long time span. If you run it for 1 month, you can have like 10,000 years worth of simulation time. The 24 hours per model year it is 24 hours for a comparable ocean atmosphere GCM, which was made in 2012. So, instead of 6 minutes, it takes 24 hours. So, we are looking at 1 hour is 60 minutes. So, 10 multiplied by 240. So, this is almost 240 times more efficient in terms of the running times. So, this actually becomes suitable for long term simulations and a large number of experiments. Experiments meaning a large number of model experiments. What if I change my some parameter by 1%? What if I change my another parameter by 2%? What is my climate after 100 years? So, we only need to wait for 10 hours of simulation and we will have the answer. So, we can do a large number of simulation experiments. This is also good for modelers who want to do climate modeling but do not have the supercomputers with them. So, when your computational resources are limited, instead of saying and going after full global circulation models, which we will be not able to run anyways, we can go with suitable, does not need to be this, any suitable intermediate complexity model, because then we are capturing the essential components of the climate, components of climate that need to be modeled in the model, but we are able to run in the computational resources that is available to us. The output quality is also not bad. It is actually adequate for many applications. Of course, when we are looking at cloud microphysics, maybe this will not be suitable, but when we are looking at some longer term changes, the output is actually okay. So, all the time we do not need to go with the most complex model just because they include all equations. We can make this judgment depending on the process and also depending on the computational resources that is available to us. So, when we say how the model performs, we can compare with the observations, of course. So, this is a model result and observations. Above we have the observations of rainfall and reanalysis winds. So, we do not need to go with the numbers, we can actually do a color comparison. This is the world map, longitude and latitude, longitude and latitude. A is the observations, B is the model simulations. So, if you see the bands, color bands, general wind directions and the speeds which are denoted by arrow directions and lengths are actually quite well represented, and the precipitation is reasonably represented. It is, the model is still, even with all the simplifications and computational efficiency, the model is still capturing pretty much big big tendencies, like this blue band, high precipitation band, this green band is there, a lot of the orange band is there, green band is quite well done here, here and here, here and here, then orange band is here, orange band is here, the green band is a bit less here and more here. So, and then more here in light green, and here it is white, but you see the difference might be just a little bit on the left and right, but give or take the model are actually doing good. Then we have also another model that can be introduced, which is the climber. It is sort of called a 2.5 dimensional model. Why? It comprises of modules describing ocean, atmosphere, sea ice, and then it has land surface processes, terrestrial vegetation, and the global carbon cycle also. So, the modules basically, these all modules interact through fluxes of moisture, energy, momentum and carbon. The model geography is coarse, but it is realistic and it resolves the continents and ocean basins. So, we have like the Pacific Ocean here, then we have the Atlantic Ocean, Indian Ocean, Pacific Ocean. These are our ocean boundaries and these are the atmospheric grids. This model is suitable for multi-millennium climate simulations. So, how do they work? This is sort of the latitude and longitude, and we can see the changes in temperature through different models and sea ice cover. The model structure for this, the atmospheric component is based on a 2D statistical dynamical 2D ST model. Now, these 2D models were generally popular in the 70s, and now they are again regaining interest because they are computationally fast, computationally efficient. The simplified 2.5D atmosphere is coupled to ocean, the one-dimensional primitive equation basin models, and the land surface, which is the simplified BATS land surface scheme, and sea ice, which is a simple one-layer sea ice model. The model reproduces realistic precipitation patterns. So, the patterns is there, but the spatial detail is a bit limited because the resolution is coarse. So, the spatial detail is a little bit limited. Now, when we have a coarser model, sometimes the application and tuning also need to be strategized. This model requires parameter tuning, and this tuning is guided by some simple rules. First thing is, if we know the parameter already, so if we know some parameter value from theoretical calculation or an empirical study, so we know if R is 8.3, we will not change that. So, parameters that are known from theory or empirical studies are not used. Parameters are with the so these are not touched. The parameters that can be touched are tuned against observations, not the overall model performance. So, the model should be, parameters should be tuned so that the observations can be reproduced realistically. But also the parameters should be physics based or physically based and not based on geography only. Having said that, these models, after suitable parameterization and tuning, have been used to successfully simulate the last glacial maximum, which was almost 21,000 years before present, and also the mid Holocene, which is 6,000 years BP. These models also have been, because of all this model demonstrated the usefulness of the EMICs in general for the long term climate studies, which is good, which is what the whole purpose is. Then there is another model called the McGill Paleoclimate Model. This model is based on an energy balance model. The concept of energy balance is extended to include moisture balance, which forms an energy and moisture balance model. So, energy moisture balance model, EMBM. The model components include ocean, sea ice, land surface, and they are used to simulate the onset of glaciations. Simulations of this model have shown that the reduced solar flux leads to colder climate conditions, reduced moisture transport to high latitudes, intensification of the thermohaline circulation, and enhanced low accumulation at high latitudes. The model includes a dynamic ice sheet model allowing simulation of iceberg calving, investigation of millennial scale climate variability. It enables the study of interactions between ice sheets and thermohaline circulation. It has rapid climate change mechanisms. It is applicable to past climates, for example, the late Carboniferous to early Permian period. So, 300 MA BP. Then we have also some simplified global climate models with water isotopologues. One of them is LMDZ ISO-GCM. Now, a key goal of many EMICs is to evaluate the adequacy of parameterizations. So, one approach is to use a fully 3D GCM while reducing complexity elsewhere, for example, by having a coarser spatial resolution or simplifying the land and ocean fluxes. This allows for a targeted assessment of the specific parameterization schemes. So, this particular model is a GCM designed to study water isotopologues as traces, which is stable isotope waters which include H216O, H218O, HTO. Isotopes are transported and mixed passively by the large scale advection and the air mass flux. So, we introduce these isotopes and let them mix and transport. The model is horizontally 2.5 degree in latitude, 3.75 in longitude, has 19 vertical levels. Each grid cell is divided into ocean, land, ice sheet and sea ice. The land surface is represented by a simple bucket model, which means the evaporation is treated as a single flux and there is no distinction between transpiration, soil evaporation and the canopy interception. Now, we can, of course, when we run a model, we need to evaluate it. So, we have the annual and zonal means of d% and delta 18O d percentile per mil, and there is the difference 0, minus 10, 16, 12, 8. The solid and dotted lines are the nudged and free run models and the plus is the data. So, as we see, the model is actually quite close. So, plus sign and the model is actually performing relatively okay. So, despite the simplifications, the model reproduces the delta 18O and deuterium excess reasonably well. The synoptic isotope variability in winter at mid latitude stations is also shown. The interannual isotope variability in mid and high latitudes is also able to be reproduced. So, this is all good. The model also simulates the reduced D axis during the last glacial maximum over high latitudes, and this is consistent with observations. So, this is the LGM CLI MAP minus present day. There is the widespread stippling indicates statistically significant LGM present differences, and also this model demonstrated the usefulness of water isotopes for validating the model parameterizations. Now we have we have seen EMICs with specific limitations in parameterizations. Next, we will have a EMIC with a truncated Earth system model. Here we have a primitive equation ocean model, 2D model, then we have a ice sheet module, then we have different ocean basins, we have sea ice, we have sort of the land, and we have Greenland here, and we have different heat fluxes being exchanged. There are 19 levels here, and we have ocean model, ice sheet model, and a atmosphere model. This is a MoBidiC model. As we can see, the model links atmosphere, hydrosphere, then cryosphere, and the terrestrial biosphere. The atmosphere is a 2-level atmosphere model. Geographically, it is a bit idealistic, and there are only 2 continents, Eurasia and America, and this was made just to capture the essential features of the Earth climate. The ocean is represented by 3 zonal models: the Indian Ocean, the Pacific Ocean, and the Atlantic Ocean. Each ocean basin has 19 vertical layers and have a 5-degree zonal grid. The terrestrial biosphere covers the coverage of trees, grass, and desert, and the relative coverage is computed for each continent, and it depends of course also on the precipitation and the growing degree days. Then the model will compute the surface temperature for each surface type. This model is simplistic, and if we see the description of land as well, this model is much better suited for paleoclimate studies, although there will be limitations because we cannot use modern observational data for the present situation to evaluate this model. So, there are some limitations in testing, but it is suitable more for the climate paleoclimate. When this model was used to simulate the volcanic and solar impacts of climate since the 1700s, the results suggest that part of 20th century warming can be explained by solar and volcanic forcing, but warming since 1930 cannot be explained by natural forcing. This is important because this basically shows the influence of anthropogenic emissions in enhancing the warming. Then we have longer simulations comparing with other models. Then when we do this comparison, we can have another model which is forced by natural and anthropogenic disturbances that climber to. The EBM matches one temperature reconstruction and the climber represents another. So this kind of thing is challenge because model validation is difficult when the observed value or the observational perceived truth is also uncertain. So what do we compare the model to? But having said that, the model is useful and has shown this kind of thing, that part warming can be solar or volcanic, but warming since 1930 cannot be explained by natural forcing. So, anthropogenic forcing has caused climate change. Then these kind of models can even go as far as predicting the future release of radiocarbons from oceans. So, we have radiocarbon is produced when neutrons replace protons in, let us say, nitrogen atoms. This occurs naturally in stratosphere where cosmic rays convert delta 14 to 14C. So, anthropogenic injections of 14C occurred between 1945 and 75 due to nuclear weapons testing, with a peak between 61 and 62. Now, our 14C decays radioactively with a half-life of 5730 years. Prior to the industrial era, atmospheric 14C was in equilibrium with production balancing decay. Now, observations have shown a 2.2 to 3% reduction in the 14C to 12C ratio from pre-industrial times to 1950, known as the Swiss effect. Why? Because fossil fuel is depleted in 14C and enriched in 12C. So, a reduction in this ratio was expected. But the observed reduction was much smaller than predicted, despite a 10% increase in atmospheric CO2. This discrepancy was explained by the 14 CO2 fluxes from land biosphere and oceans driven by increasing atmospheric CO2. So, this 12C increased, but 14C also increased. So, the decrease in the ratio was not as much. Thus, fossil fuel emissions indirectly led to an increase in atmospheric CO2, despite fossil fuels did not have much 14C, because this was driven by increasing atmospheric CO2, 14 CO2 fluxes were increased. Now, when we combine an EMIC with a 3-box terrestrial biosphere model and a box diffusion ocean model to study the radiocarbon fluxes, what we see is that atmospheric 14C reached a minimum around early 21st century. And atmospheric 14C is projected to increase in the future. So, if we have this year 1898, 2000, 2100, we have the atmospheric 14C mass and we see fossil fuel burning, both fossil fuel burning and land use change, and if there was a explosion. So, the percent change atmospheric 14C percent should decrease. Atmosphere to ocean radiocarbon flux should also decrease. Future increase can occur when cosmic ray production exceeds uptake by land, biosphere and ocean. The model shows that oceans will become a net source of atmospheric 14C around 2030. And this kind of results can give a valuable test for more comprehensive climate models and the representation of the global carbon cycle. Most climate models focus on future climate prediction over decades to 2100. The emphasis is primarily on anthropogenic GHG increase. Long-term climate change, including periods beyond influence of human, can also be studied by simpler models, especially the EMICs. And then of course, one question can be if the interglacial period may end or begin. Now, early studies in 1970s suggested a new glacial period might begin. Geological evidence suggested that last two interglacial periods lasted about 10,000 years. So, based on this, early projections suggested that present warm period would basically end. In the mid 1980s, a simple ice sheet model predicted an interglacial period of 50,000 years and a glacial maximum at 65,000 years after present. Now, more recent models used an improved knowledge of future astronomical forcing, and then there were more predictions happening. So, for example, the June insolation will remain below 25 watt per meter square for the next 25,000 years. Then what they did is they make simulations for climate evolution under known future orbital forcing, which is 3 GHG scenarios: low CO2 210 ppm, geologically expected CO2, atmospheric CO2 750 ppm, which is high. The results showed that there was major differences between very low CO2 case and other cases. Both moderate and high CO2 scenarios predicted very long interglaciers. At 750 ppm, ice volume reaches 0 and Greenland ice sheet melts completely. The next glacial maximum occurs only after 100,000 years. So, the early 70s production were actually more akin to the low CO2 scenarios. Now, we can come to some questions, which is why climate models of intermetric complexities are used. This is because we are sort of summarizing this. So, climate models must address many different questions. These questions span multiple spatial and temporal scales and varying levels of complexity. So, this is sort of the level of complexity. No single type of climate model can meet all needs well. Therefore, different model types are developed to address different purposes, which makes sense. Now, meeting diverse information needs, disaster risk management and climate change adaptation will require information on climate extremes, information on climate change. At the global scale, we have business and economies involved. So, we have broad climate trends, local weather details. At local scale, we have local climate information. So, climate modelers will develop modeling schemes to address these diverse but interconnected needs. So, sometimes we need to go for simplified models, sometimes we need to go for highly complex GCMs, and then the intermediate complexity models somehow fill the need in between the two. With this, we come to the end of this lecture. We will continue in the next lecture. Thank you.